Tashidak everybody. So today I am going to discuss the last chapter of first book, that is electromagnetic wave, and this is a very short chapter. However, this is a very important chapter because this chapter includes the entire first book. All right. So first, what I would like to do is I would like to do a brief introduction about the chapter that is electromagnetic waves. Right. So let's start something like this, right? We say that electric currents, right? We say that electric current give rise magnetic fields. So we say that electric currents, right? So I say current give rise magnetic fields. Magnetic fields. All right. We say that current give rise magnetic fields. And we have also done that the changing magnetic field, right? Current give rise magnetic fields, and that is very well studied in chapter number 4. We talk about Boyle-Sievert law and Ampere-Circular law, and then we also discussed that the changing magnetic field give rise a current, that is give rise electric field, right? That means what we have studied is in chapter number 6, that is electromagnetic law of electromagnetic inductions, says that there will be a EMF induced when there is a rate of change of magnetic flux. Magnetic flux. And when I say this is EMF. EMF means voltage. When I have a voltage, and voltage is going to be electric field into distance, or electric field into length. So this implies that the changing magnetic field give rise electric fields. Now the point is, the question is the changing electric field give rise magnetic fields? All right. So here we say that a changing magnetic field give rise electric field. The converse is it possible to give a electric field? Magnetic field out of changing electric field, right? So this is very important questions, and this was studied very well by Maxwell. All right, and he says that yes, it is possible to produce magnetic fields out of changing electric fields. All right, so this was studies, and after studying this, all right. After studying this, he formulated what we call as Maxwell 4 equations. Alright, Maxwell 4. So in a way, when we discuss Maxwell 4 equations, we would like to combine electricity and magnetisms. And that is, we would like to make it a single a concept or a single subject, that is what we call as electromagnetisms. Alright, so electromagnetisms which involves both electricity as well as magnetisms, right? So what is the contribution of Maxwell is that he says that yes, a changing magnetic field, a changing electric field can give rise what we call as magnetic field, right? Changing electric field give rise magnetic field, and this is what he studied this under a displacement current, and he studies this inside a capacitors. Actually, this is not there in our syllabus. Last time it is there, but this time it has been deleted. However, I am going to say that this is these things are taking place inside capacitors. All right, and he coined the term called displacements. All right, so this is what we have, and then this is a Maxwell equation. You can write a Maxwell equation in different forms. So this is what we have done in the Maxwell equations. So this is the point, right? So here I would like to write here this current can be written as this is the equations, right? This equation, this is what we call as a current. And if there is a current, then current produces magnetic fields. Alright, if there is a current, we get a magnetic field. So in a sense that changing electric field give rise magnetic field. So this equation tells that the changing magnetic field produce electric field, and this equation tells that changing electric field give rise magnetic field. And now once he correct the Ampere second law, and now this becomes Ampere Maxwell equations. All right. Now this is what we call as Maxwell 4 equations. So this entire 4 equations give rise, explain entire electromagnetisms. All right. So now there is nothing like the electricity or magnetisms all in a one. That is what we call as electromagnetisms, and everything can be answered, everything can be explained under these 4 equations. So this is what we know. This is done in chapter number 1. That is the Gauss's law, right? This is electric flux, and this is how it is electric flux is given. This is the magnetic flux. Magnetic flux in case of Gauss's law is 0. Magnetic flux, that is Gauss's law for magnetism, is 0. We talk about this is Faraday's law of inductions, and this is last, that is Ampere Maxwell equation. So actually we have this in a syllabus, however this year it has been deleted, right? So this gives you, and then one of the most important contribution of Maxwell from this equation, what we can tell is that this equation predicts the existence of what we call as electromagnetic wave. This equation tells that there exists something called electromagnetic waves. There exists something called electromagnetic waves. All right, and we would like to study. In this chapter we would like to study the sources of electromagnetic wave, nature of electromagnetic wave, and the wide spectrums of electromagnetic wave. So 3 things we are going to study: sources of electromagnetic wave, nature of electromagnetic wave, and then the range of electromagnetic wave. That is a big, large or huge, wide spectrum of electromagnetic waves. So this is what we are going to study. And the displacement current is not there in our chapter, not there in our syllabus, right? So this is all about introductions. And then one thing I would like to give you is the Maxwell he predict the existence of what we call as electromagnetic waves. All right, what we call as electromagnetic wave, and from his equation we can tell that there exists what we call as electromagnetic waves. There exists what we call as electromagnetic waves. All right, and he says that the speed of electromagnetic wave would in a vacuum would be equal. This can be predicted from his equations, and then his theory was experimentally proved by Hertz. All right, and Henry Hertz experimentally produced electromagnetic wave in his laboratory, and therefore he was the first to demonstrate the existence of electromagnetic. The prediction was done by Maxwell, and then demonstration was done by Hertz, right? So this is what we talk about, right? So Hertz was the first scientist who experimentally demonstrate the existence of electromagnetism. After Hertz, people feel that, people now confirm that, scientists confirm that there exists what we call as electromagnetic wave, and the light, that is visible light, is also electromagnetic wave. So this is what we are going to study now. All right. So this is what we are going to study. So now first what we are going to study is the sources of electromagnetic waves. So first we would like to study the sources of electromagnetic waves, right? We are not going to study detail, but however we will study just surface, right? So to study the sources of electromagnetic waves, we say that a charge, right, which is at rest, charge at rest produce electric field. Charge at rest could produce electric field. Alright, charge at rest could produce only electric field. And then a current, right? So current, that is, let's say a steady current, or a charge moving in our straight lines, charge with uniform velocities, could able to produce only magnetic fields. Alright, so charge at rest could able to produce the magnetic fields, and the charge that is moving with a uniform velocity, that is the steady current, could produce the magnetic field. However, in both the cases, right, in both cases, I say either charge is not changing with times. In both the cases, the electric field is either electric field is not changing with times, or magnetic field is not changing with time. In both the cases, electric field and magnetic fields are not varying with times. In both the cases, electric field and magnetic fields are not varying with time. They are constant with times. Electric field, the magnitude of electric field and the electric fields are not changing with time. So this is very, very important, right? That is why we can't talk about what we call as electromagnetic waves, right? So now if I accelerate charged particles, all right? Let's say now accelerated charged particles. And accelerated charged particle means, how can I accelerate charged particles? The question is, how can I change oscillating, right? If I let a charged particle to oscillate, oscillating charged particles. And oscillating charged particles, right? These oscillating charged particles or accelerated charged particles give rise to time varying electric fields. This give rise to time varying electric fields. This phenomenon, that is oscillating charged particles. Oscillating means if I vibrate, alright, if I vibrate charged particles, right? If I vibrate the charged particles, which give rise a time varying electric fields. Alright, time varying electric fields. Alright, so if electric field is changing with times, alright, if electric field is changing with time, which give rise a time varying magnetic fields, which give rise a time varying magnetic fields. In a way, what we are going to see is, we are going to see a time varying electric field and time varying magnetic, that is oscillating. That means we see oscillating electric field and oscillating magnetic fields. So what we see is, we see oscillating electric field and we see oscillating magnetic fields. Oscillating electric fields give rise oscillating magnetic fields, and oscillating magnetic field give rise oscillating electric field. So they regenerate each other. That means they regenerate each other, right? This is what we talk about. Each other means alright, time varying electric fields. I'll write you like this, right? Time varying electric field give rise time varying magnetic fields. Time varying magnetic field give rise time varying electric fields. So this is what we talk about. And this is what we call as electromagnetic wave. And this is how electromagnetic wave is generated. So they couple each other. That means electric field and magnetic field couple each other. Electric field and magnetic fields couple each other, right? They try to produce each other and then propagate in a space. They try to produce each other and propagate it in a space. So this is how, this is not, we are not going to study detail about the sources of electromagnetic, this is how we could see that yes, the electromagnetic wave can be produced in this way. Alright. And then we would say that while propagating electromagnetic wave, it associated energies. What kind of energy? Magnetic energy as well as electrical energy. So the propagating electromagnetic wave are also associated with the energy, and that energy involves electric energy as well as magnetic energy. That we should keep in mind. And then we will say that what about when I oscillate charged particles, it has some frequency, right? And the frequency of electromagnetic wave, right? So this couple each other, this produce what we call as electromagnetic wave. All right. And the frequency of electromagnetic wave, is equal to the frequency of oscillating charged particles. Frequency of oscillating charged particles. So with what frequency electromagnetic wave can be produced is equal to with what frequency charge is oscillating. So this is what we talk about, right? So let's say, is it practically possible? Yes, right? But for visible it is a little tough. Why? The reason is that what about the frequency of yellow light, right? Frequency of yellow light is something like 6 into 10 to the power 14 hertz. This is in a second, this many oscillation is taking place. However, a modern electronic, right, device could oscillate a charged particle only up to 10 to the power 11 hertz. So that means this comes in a short radio wave, right? So that therefore practically it is not possible to produce a yellow light or green light out of oscillating charged particles, right? Why? Because this is due to technological limitation, right? Because of a technological limitation, because of we don't have any such an instrument which could oscillate charged particle up to this frequency. So therefore we won't get a yellow light. All right. So this day we could able to produce this much. So therefore we could able to produce only radio wave, short radio wave, microwave, and all. Right. So this is what we talk about. Right. So this is the sources of electromagnetic wave. This is what we talk about, the sources of electromagnetic wave. Now I would like to study the nature of electromagnetic wave. So sources of electromagnetic wave. Now we would like to talk about nature of electromagnetic wave. So now we would like to study a nature of electromagnetic wave. So we say that electromagnetic wave is a transverse wave. So electromagnetic wave involves the oscillation of electric field and oscillation of magnetic fields. Alright, electromagnetic wave involves the oscillation of electric field and oscillation of magnetic field. They couple each other. That is what we talk about, right? And in case of electromagnetic wave, electric field is oscillating and magnetic field is oscillating. And how they oscillate, right? So electric field and the magnetic fields are perpendicular to each other, right? The oscillation of electric field and the magnetic fields they oscillate perpendicular to each other. And how they propagate? They propagate in a direction perpendicular to the oscillation of electric field and magnetic field. So this is what we have. I'll show you one diagram. So this is how you see it, right? This is how you see it. Alright, this is how you see, right? Electric field oscillation and magnetic field, they are perpendicular to each other, and a propagation is also perpendicular to the oscillations. Propagation is also perpendicular to the oscillation of electric field, and so in a way I can say that all the three components, that is the velocity components, and then electric field components and the magnetic field component, all are perpendicular to each other. So that is one very, very important, right? So now the point is, how electric field is oscillating and how magnetic field is oscillating. If electric field is oscillating in a x directions, then magnetic field has to oscillate in a y direction. So this is what we have. So the electric field, this is the electric field at any instant of time t. This is the electric field at any instant of time t in the x directions, in the x axis. This is equal to E naught sine k z omega t. So z means it is traveling along a z axis. It is oscillating in a x axis, oscillating in a x axis. Electric field is oscillating in the x axis, and propagation is along z axis. Propagation is done along a z axis. And E naught is amplitude. E naught is amplitude of electric field. E naught is amplitude of electric field. And then we have a magnetic field is also oscillating. So magnetic field is oscillating in a other direction, that is y axis, right? So I just say magnetic field at any instant of time t. This is magnetic field at any instant of time t, which is given by B naught. B naught is amplitude of magnetic fields sine k z. Propagation is along z axis. K z stands for the component along propagation component, right? And omega t. T is any instant. So this is what we talk about, right? And this is also known as, this is also called amplitude of magnetic fields. Amplitude of magnetic fields. Alright, now we say that, now what is omega? Omega is angular frequency. Angular frequency. And t is instant of time t, right? At any given time t, at any given time t. And k is wave number. K is what we call as 2 pi divided by lambda, and k is what we call as wave number. K is what we call as wave number, right? And then from these equations we can also tell that the speed of electromagnetic wave can be written as omega by k. Dimensionally it is also equal to omega by k. Omega is angular frequency, k is wave number, right? So therefore look at here, this can be written as, what is omega? 2 pi mu, and what is k? 2 pi by lambda, and this is equal to lambda mu. So therefore speed in a vacuum, the speed of electromagnetic wave can be written as this. This is the speed of electromagnetic waves. Alright. Or else I can say that this C is also equal to, omega is also equal to Ck. Omega is also equal to Ck. Alright. Omega is also equal to Ck. And then we can also express in terms of permittivity, right? So again I can say that C is also equal to 1 by root of mu naught, and so this equation tells that speed involves both permittivity and permeability, right? So this is permittivity and this is permeability. In vacuum, right? This is what we have. Alright, this is what we have. Alright. So therefore we say that speed of electromagnetic waves. So this also tells that irrespective of whether it is a long wave radio wave or a short radio wave or a gamma radiations, all the electromagnetic wave has a constant speed. C is a speed of electromagnetic waves, and the speed of electromagnetic wave is not defined by the wavelength or frequency, right? Speed of electromagnetic wave is defined by a medium, right? This is what we talk about mediums. If I change the mediums, then speed of electromagnetic wave is going to change. So that's why, because this is the factor is this property, right? Permittivity and permeability. So that is one very, very important point, right? And then the speed of electromagnetic wave is also given in the terms of amplitude of electric field and amplitude of magnetic field, right? So I would like to write here. All right. So this is what we have, right? B naught is equal to E naught divided by C, or C is equal to. So this is very important expressions, right? This is also very, very important expressions. And B, right? Magnetic field, the oscillation of magnetic field and the oscillation of electric field is all given by these expressions. All given by this expression, right? All given by this expression, right? So the speed of electromagnetic wave is the ratio of amplitude of electric field to the magnetic field, right? So therefore, since speed of electromagnetic is very high, so the amplitude of electric field is extremely very high compared to the amplitude of what we say a magnetic field. So we say that, roughly speaking, in vacuum this is going to be this. All right. So that means the speed of the amplitude of electric field is 3 million times the amplitude of magnetic fields. Amplitude of electric field is 3 million times the amplitude of magnetic field. So that means the amplitude of electric field is very, very high, right? And then I told you just now that the speed of electromagnetic wave vary with the mediums. So this is what we talk about. So V can be written as, this is what we talk about, mu epsilons, right? So that's what we talk about. This is what we have, and this is what the speed of electromagnetic wave is this, and it is independent of wavelength. However, it varies from medium to medium. That's what. However, it varies from medium. Why? The medium, the different medium has a different permeability and permeability, right? Now again, one very important points. All right, that's maybe next chapter we'll discuss. Electromagnetic wave carries energy as well as momentums. Just now we talk about electromagnetic wave. When in introduction part I talk about electromagnetic wave has energy, and that energy involves both electric field and magnetic field, right? So, and then it has a momentum, and then it has a pressure, right? Electromagnetic pressure, right? If it has a momentum, then it has a pressure. If it has a momentum, there is a transfer of a momentum taking place. There is a transfer of momentum taking place when an electromagnetic wave falls on some surface. So that is what we talk about. So I say that for electric field, E, alright? If I say for electric field E, energy involved, that is done, right? I say that if in a medium or whatever, right, if I have an electric field E, the energy density is going to be, alright, let's say in a capacitor, if I have an electric field E, alright, then energy density would be half epsilon naught. This is the energy. This is the energy, right? This is the energy involved in an electric field E. Electric field E is associated with the energy density this much. Electric field E is associated with the energy density this much. Now if I say, if I have a magnetic field B, for a magnetic field B, for a magnetic field B, that means energy density alright, so energy associated with the energy magnetic field B is this much, right? So energy associated with I just say energy associated with energy B this much, and energy associated with this. This is what we have, right? So if I say so, then electromagnetic wave, which is nothing but electric field and oscillation of then I say electromagnetic wave, which is nothing but oscillation of electric field E and magnetic field, is also associated with energy, right? Associated with a non-zero energy density, right? Non-zero energy density. So I say that it carries the energy density. Right? So that means it has an energy density. So therefore, when a light or when an electromagnetic wave falls on a certain objects, and this transfer energy, this will transfer energies. That's one very, very important point. Now relate to this. Now if I say I have a plane surface which is perpendicular to the propagation of electromagnetic waves. I have a plane surface which is perpendicular. I have a plane surface like this. This is a plane surface. I have a plane surface which is perpendicular to the propagation of electromagnetic wave. So this is how electromagnetic wave is propagated, right? This is electromagnetic waves, alright? I have a plane surface which is perpendicular to the propagation of electromagnetic waves. And then what happens is that on a plane surface, electric field is oscillating, right? Let's say if electric field is oscillating like this, and magnetic field is oscillating like this. So electric field oscillates like this, and magnetic field has to oscillate like this. Then what happens is that the charged particles on a plane surface undergoing oscillations, and that means it gain energy. Charged particle on a surface of a plane surface gain energy, and they start moving, right? They start moving. That means they start moving. It involves the transfer of momentum, right? It involves why? Because electric field is oscillating like this on a surface, magnetic field is oscillating on a surface, and then because of which the charged particles lying on a surface gain electrical energy, right? And charged particles lying on a surface undergo oscillation, right? So therefore it gains what we call as momentum, right? This is what we call as momentum. So thus, because of which charged particle on the surface gain energy as well as momentum. So this is what we talk about, and maybe a detailed study about this we'll do in the next class, right? This is what we talk about, and in a way, if there is a transfer of momentum taking place, and there must be a pressure taking place, right? This is what we call as radiation pressure, right? And then one more I would like to do is say total transfer, I say the total energy transfer, transfer to a surface in time t is u. All right. Then momentum transfers, total momentum transfer or deliver to the surface would be equal to, this is the momentum u divided by c. So this is how we talk about momentum transfer. This is what we talk about momentum transfer, right? So these all are a brief nature of electromagnetic wave. So that means when we talk about electromagnetic wave, there is momentum, it involves the energy, it involves the momentums, and then it involves a transfer of energy, it involves the transfer of momentums, pressure also, right? So this is what we have. So this is all about this. Now what we are going to discuss is the wide range of electromagnetic waves. So now we will try to talk about a nature of wide range of. So before that, this is what we talk about. Before that, I would like to explain you this, right? So this is electric field oscillating, and this is the magnetic field. These two are perpendicular. Electric field is oscillating in x directions, all right, and magnetic field is oscillating in y directions, and propagation is done in a z direction. This is what we talk about. So this tells the nature of a propagation of electromagnetic wave. All right, and one more I will tell this. This is better writing, right? This is electric field. This is electric field. This is magnetic field, right? And this this is one wavelength, and then this is one wavelength, same, right? This is what we talk about, magnetic field, electric fields. Again, this is what we have, right? So this is electric field, this is magnetic field, and this is how propagation takes place. Wavelength, this is going to be a wavelength, and both the wavelength, the oscillations, the time period for both the electric field and magnetic fields are equal, right? So this is what I explained you, right? Alright, graphical representation of electromagnetic. This is electric field and this is magnetic field, and both oscillate each other, right? So this is how propagation takes place. Alright, now I would like to do a last part of this chapter, that is electromagnetic spectrums. Alright, we are going to study electromagnetic spectrums. So we talk about electromagnetic wave. We talk about electromagnetic wave in a very first part, that is during an introduction part, and I say that the Maxwell was a scientist who predict the existence of electromagnetic wave. Actually, it is there, all right. People never knew that a light is electromagnetic wave, all right. So now, now, once the electromagnetic wave was experimentally demonstrated in a lab by Hertz, now and the nature of electromagnetic wave, when we study the nature of electromagnetic wave, we get to know that electromagnetic wave consists of a wide range. All right. So we talk about a wide range of electromagnetic waves. All right. So this range, huge range. The range involves the wavelength, right? The wavelength from 10 raised to power the range from gamma radiation to long radio waves. So when I split entire electromagnetic spectrums into different groups, we have a different electromagnetic waves based on its the wavelength and the frequencies. So alright, so the highest frequency and a shortest wavelength is what we call as a gamma. Alright, gamma radiations. Yeah, so this is a gamma radiations. So that is the range of electromagnetic wave goes from 10 to the minus 15 meter to 10 to the power 10 meters. So this is of huge range. This is of huge range. Look at here, right? Alright, this is of huge range. Alright. So this is what we have, right? So the first, the longest, the shortest wavelength and the highest frequency is gamma radiation or gamma ray, and then followed by an X-ray. Alright. And then we have ultraviolet radiations, and then we have what we call as a visible light. So visible light, that is the light we could able to see, also comes under electromagnetic wave, and this involves a very short range, right? That goes from a violet to a red. And then we have infrared, and then we have a microwave, and then we have a radio wave. Even in case of radio wave, we have a short radio wave, and television FM radios, AM radios, and long radio waves. So these are the different range of electromagnetic waves. All right. So we have, and when we talk about visible light is a range of a small range of electromagnetic wave. That range, the wavelength goes from 400 nanometer to 700. That's the range is extremely very small compared to the range of entire electromagnetic wave. So this is what we have, violet, and this is what again I just say, right? This is gamma radiation, so gamma ray. All right, so gamma ray, highest energy that we are going to study in the next chapter. This is having the highest energy, and then we are going to have a radio wave. All right, that's goes to the wavelength is 10 to the power 6. All right, so this is what we have, and then I have this. Look at here, look at the wave, right? So this wave frequency is very high. As you go in this direction, frequencies start decreasing and wavelengths start increasing. And energy is also decreasing. Look at here, energy increases in these directions, and the frequency increase in these directions. Wavelength increase in these directions. All right, wavelength increase in these directions, and energy decrease in this direction. That you should keep in mind. All right. Oh, this is what we have. So this is again we have the gamma, extremely very small, that involves in a nuclear, very small. All right, and then we have X-ray. All right, that talks about uses and all. Right. Then we have ultraviolet radiations. All right. Whenever we talk about ultraviolet radiation, we talk about we know about ozone layer, and ozone layer is one that will not allow ultraviolet to pass through it. And then we have a visible light. Then infrared. Infrared is heating effect that we talk about. Heat wave. All right. And then a microwave. Then radio waves. Right. So radio wave involves all this. Right. So this is what we have. And now we will study this. This is a radio wave. This is a long radio wave, or this is a radio wave. And normally radio waves are produced by a rapid acceleration and deceleration of electron in atom. So that is how we could able to produce this. I allow a charge particle oscillate, and then this is how it produced. And the detection is receiver error. This is not very important for exam. This is just for your understanding only, right? And then we talk about microwave. All right. So klystron valve and the magnetron valve. That is how it is going to produce. And this is detection is done by a point contact diode. And then we have infrared. Infrared is the vibration of atoms and molecules. So we talk about this. This is done in class 11, right? The vibration involves the heat. All right. So let's talk about, right? And then we talk about visible light. Visible light we talk about, again you learned this in class 11, right? When the electron undergoing transition from a higher energy level to lower energy level, that emission of light taking place. So this is what we talk about. And then we talk about ultraviolet, the inner shell electron in a atom that involves, these things are not easy to understand. That just for our understanding I'm telling you, right? And then we talk about X-ray, and then we talk about gamma radiation. We'll study this, right? This involves only during radioactive decay. And the range we talk about more than 0.1 millimeter or more than 0.1 meter, it is all radio wave. Between 0.1 to 1 millimeter, it is microwave. Between 1 millimeter to 700 nanometer, it is infrared. Between 700 nanometer to 400 nanometer, it is visible light. Between 400 nanometer to 100 nanometer, 1 nanometer, it is ultraviolet. And this is 1 nanometer to 10⁻³ nanometer, it is X-ray. And less than 10⁻³ nanometer is what we call as gamma. So gamma has the highest energies. All right. So this is again we have all right, frequency, radio wave, all right, oscillating charge particle, same, right, microwave, and then infrared, and then visible lights, then ultraviolets, and then X-ray, and then finally we have a gamma radiation, right? So this is what we have. Again we have all repetition. Alright, now what I'm going to do is I would like to study the application of those things, right? Application of those. We are not going to study detailed application about those electromagnetic spectrums. We will study a little bit about the application of each electromagnetic spectrum, right? So gamma radiation, the gamma ray or gamma radiations, right? So we talk about how it is produced, and then the range of wavelength. So that I'm not going to. I will focus only on an application part. And the gamma radiations is normally used in a medical purpose. In a medicine, it is going to use. So this is mainly used to cure cancer, right? So that means when a gamma radiation is allowed to focus, right? If I allow a gamma ray to fall on cells and tissues, it is that's tissues and cell is going to destroy. That means this is how you remove a cancer cell, right? And then it is also used to sterilize the medical equipment, right? Once you expose medical equipment to gamma radiations, and then all the bacteria can be killed, right? And this is also used to kill bacteria in a food. This is as far as gamma is concerned, right? Now X-ray. So X-ray, I know it is very important, right? Very significant in diagnostic tools. That is, we talk about X-ray. When it helps us to see whether the bone get fractures or not, right? So diagnostic tools. How imaging internal structures. All right. If you are exposed to a X-ray, and then if you do a photographic, right, X-ray, then you could see the bones, right? And then X-rays are also very much used to study studying the structure of atom. That is what we call an X-ray crystallography. That is one big branch of physics called X-ray crystallography, and that help us to study the structure of atoms and molecules, right? And then it is also used for curing cancer treatment, right? Then we have UV radiations, right? And UV radiations are again used in the water treatment, right? So Why? Because when the UV ray, when the water is exposed to a UV radiations, the UV radiation kill all the germs in the waters, and that purify, right? And this is also fine in fluorescent tubes, right? And then this is one thing, right? Tanning of the skin is all because of UV radiations. All right, that means blackening of skins is all because of UV radiations. And also UV radiation is also very much used in eye surgery. That is what LASIK, laser assist in situ or cataract, right? That's very difficult to pronounce. And this image is very useful for eye surgery. Why? Because this focus, right? Eye is very small, and then you can't do surgery like what you do inside body, right? So therefore, what we do is we just send a UV radiation, and this is normally cataract, right? Eye problem, then this can be done, right? And then visible ray, no doubt, this is without visible light we can't see, right? So it is seams and optical fibers, and then communication purpose. All right. So now next is infrared. So infrared is without infrared radiations, there is no heating take place, right? Infrared radiation is nothing but heat radiations. So therefore, it is used for radiant heaters, right? If I somehow could generate infrared radiation, that means heating taking place. All right. And we also say that how glass house get warm, right? Why? Because glass house doesn't allow infrared radiations, right? So it taps the infrared radiations, right? So that is why that, like carbon dioxide, if the carbon dioxide, the percentage, right? An amount of carbon dioxide increases in the Earth's surface, then carbon dioxide, the nature of carbon dioxide is that it taps infrared radiations. If it taps infrared radiations, then the temperature of Earth is going to raise, right? So this is what we have, right? So whenever we talk about infrared, it involves heat, right? And then therefore I say that infrared detectors. All right. So this is what we have, and used in the Earth satellite and both for military purpose, right? Military purpose means you can have infrared. You could see this image, right? Infrared thermal imaging, right? So that's one very important, right? And then it is also used in the remote, right? Remote sensing, right? All the remote sensings involves infrared radiations, right? So when you tap remote sensings, you don't see light, but then infrared radiation is produced, and then signal can be detected. And then we have microwaves. So microwaves normally used in radar systems. Are used for navigation, air navigation purpose, right? And then microwave is also used in the oven, right? For cooking purpose, right? Ovens, we normally produce microwaves, and then the microwave, the frequency of microwaves match with the frequency of a liquid, and then under resonant, then heating take place. Then the oscillation is taking place, due to which heating take place. And it is also used in the satellite communications. Now last, that is what we talk about radio wave. This is radio wave itself is so huge, right? But then just for our simplicity, the radio wave involves short radio wave to a long radio waves, and it is very essential for communications. Whenever we talk about communications, it involves the radio waves. All right. So before last year, we have one small chapter called communication systems, right? And that involves only radio wave, but this time it has been removed. So the radio wave, the application of radio wave is radio and trailing communication systems. All right. So with this, we come to an end of this chapter number 8, and with this we come to an end of first book. Thank you.